Hello, Mr. Sorrentino here again. I'm doing another one of these videos for our Math 31 course. And this is the first section of the last chapter that this course covers, which is chapter 6, and this is 6.1, Systems of Equations in Two Variables. Um, when you deal with situations like this, essentially what we're looking for, when we want to solve a system of equations, as it states right here, the solution from a graphical standpoint is given by the coordinates where the two lines intersect one another. So if I would graph each of the lines and see where they intersect, that intersection point would be the solution. The issue is that there are some problems with graphing it, and we're going to see those a little bit in this part right here. Notice that I have a graph set up um, going from -5 to 5, both for the x's and the y's, and I actually have 1, 2, 3, 4, 5 spaces for each full unit. So this is basically going by fifths or 0.2s. So it's always a good idea to have an idea of what the scaling of your graph is, so that you have an idea of where you can place points a little bit more accurately when you actually get to graphing. But sometimes, no matter how well you try to prepare for that and make it as precise as possible, you may have a scaling that doesn't just work really well with the equations. Case in point, right now both of these equations are linear equations. They're written in more of the standard or expanded format, and so for me to graph them, and as we've done before, we also put on the graphing calculator. But even to do that, I had to solve for y. When I solve the top one for y, I get y equals -4/3 x minus 2/3. This graph is not set up to go by thirds; it goes by fifths. So 2/3 is about 0.66666 repeating. So somewhere between 0.6 and 0.7. And so I could probably say for -2/3, going by fifths, I'd go down 1, 2, 3, that'd be 0.6. Next one would be 0.8, 0.7 would be somewhere in between. So maybe roughly somewhere around here. But that's a speculation, that's a guess. I can't say for certain that I'm doing this exactly right. I might be off a little bit. And then I could do the rest of the points, which means if I follow the slope, I go down 4 and right 3, or I could go up 4 and left 3. I might want to do a little bit of each. If I go by full units, it might be tough. But since the x and y scales are both going by fifths, I could count this little boxes as well and say, okay, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. That gives me nice 3 points here. I'm going to use the ruler instead of plotting a bunch of other points. Try to get it all lined up here. And sorry about that. I had a little glitch and it turned off, so just reshooting here. So I graphed a line at this point right here. So there was some guessing I had to do for this one because of the fact that this graph isn't really scaled to go by thirds. On the other hand, the second one, if I were to write this in slope-intercept form, I would have y equals a positive 2/5 x minus 12/5. This is a little easier to graph because my graph is going by fifths. So I could say, okay, down 12/5, I just have to count 1, put it here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12/5 would be here exactly. So sometimes it does work out for us, sometimes it doesn't. So here's the point here. And again, since my x and y axes are scaled the same, I could use the small blocks I have in here when I use my slope of 2/5. I could also go up 2 full units, right 5. I just don't have as many points that way. So I'm going to do 1, 2, 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5. I'm going to pull out the ruler again. Now, if I graphed it right, it looks like right here is where they intersect. It looks like it intersects at 1, -2. And I can actually confirm by either plugging those coordinates in, 1, -2, or using the calculator. Didn't want to do that. I want to do that. So the solution for this was 1, -2. It says I can confirm by plugging 1 and -2 in for x and y respectively, and seeing it does work for both equations. I'm not going to do that in this video. You're welcome to do that to do your own checking. Or I could also check it on the calculator just to briefly go through that, although I do give you the information on your notes already. This picture over here, I'm going to demonstrate it really briefly. So I'm starting off now. These are the equations I got when I solved for y and put it in the slope-intercept form. And so if I would graph them, and I set up my window to be very similar to this, going by -5s. I'm not going by tenths so much. I don't want to see too many like dots on my axes. As long as I have the min and max the same, the scaling doesn't matter quite as much since the calculator can actually do calculations of that matter. And I'm going to graph it. Now these colors are reversed. This one has the blue one being the first one and the red one being the second. And I can see the intersection point right here. And I want to make sure there was a typo. It's to be 4/3 x, not 4/5 x. So let's graph that again. It wasn't showing up at the right point. I mean, because I know 1, -2 is the correct one. And sometimes little things like that happen. So that's why I'm not going to edit this one out. It's good to see, like, like you recheck things as you do this to make sure that, things are working out the way they're supposed to. It looks like 1, -2 is the right answer. I can verify that by going to my calculate menu. And like I had done in the problems prior in this course, I can find where these two graphs intersect each other. Now with lines, it's pretty easy because they should intersect at one point if they do intersect at all. So I'm just going to choose the line. I don't really have to guess. I mean, if I want to, I could perhaps move this closer to what the intersection point is, but it's not necessary. Like you can see, I get the intersection to be 1, -2. So that verifies the solution to it. So now, but as I mentioned before, it didn't happen so much in this one because of the fact that, it's not going to be way off, but sometimes the scaling of your graph might make it difficult to graph as exactly. And what if the solution isn't meant to be, integer coordinates? I mean, I could have, fraction coordinates or even irrational coordinates if necessary. Probably won't see that much with linear equations, but it's possible. So graphing can be difficult because your graph may not be completely able to show show the answer as accurately as you need to see what the right answers are. Because again, if 1, -2 didn't work, well, I would expect that I would expect the x to be near 1 and the y to be near -2, just not precisely those. So we use algebraic methods, which is what the main focus of this particular lesson is going to be on. But we also have to be aware that we have situations like this where we have lines that intersect in one point and therefore we'll have one and only one solution. There are two other circumstances, special circumstances, that do pop up from time to time and you need to be aware of. And on page 2 of your notes, we do mention these two other circumstances. A situation like the example we just did is called consistent and independent. That means I have one and only one solution. So that's what the consistent and independent mean. One and only one solution. And lines often will intersect at one spot, but they also could do two other things. I could have the lines be parallel, which means they would never intersect, which means that there's no solution, and we would call that inconsistent and independent. Now, I can see that graphically really easily. The question is, how would I see this algebraically? We'll look at that momentarily. I could also have two lines overlapping. Sometimes, I mean, if it's written in slope-intercept form, and if you simplified all of your fractions, it would be very noticeable because you would have the exact same equation. But if they're written in an expanded form we saw in the example, it may not notice it right away. It's going to tend to happen, and something happens in the process of solving it algebraically. It's going to let you know that as you do it. But we can have that situation where all points on one line are intersections, so they're infinite solutions. We would say that's consistent and dependent. So basically the line itself is the solution because there's a bunch of ordered pairs that would make that work. It doesn't mean every ordered pair. All points, and I should say really here, emphasize on the line, are solutions. They're all intersections too, but so there's infinite solutions. I have to be able to be aware of those two cases as I do my work for these and recognize them when I see them. So let's start looking at the two methods that we do make use of as we solve this. The first one is going to be substitution. The two methods that we have to solve these, let me scooch that down just a little bit, as I mentioned before, are substitution. The other one's going to be called elimination. Sometimes they call that linear combinations as well. So if you ever see a direction, although it shouldn't happen in this course, but in future courses, you're asked to solve a system of equations using linear combinations, it's the same thing as elimination. But substitution or elimination, it doesn't matter which one you use. There are some circumstances that are better equipped for substitution and others that are better equipped for elimination. You could use, them interchangeably. You could use them, based on the situation, on your decision making. You could choose to use one only or the other one only. It doesn't really matter to me which one you use, as long as you're using a correct method and make the right conclusions when special circumstances arise too. That's all that concerns me. So I'm not a stickler for which one you typically use. And even with that, like some of the questions they even ask in my math lab, they say, okay, use substitution. Well, if you use elimination, it doesn't matter anyway because all you're asking for is the answer. So, but essentially, substitution works best under part A, as you see here. I have one of the equations already solved for one of the variables. When I have a situation like that, that's really set up to do a substitution. Because what's going to happen is, if I didn't have the equation already solved for y or x, whichever the case I choose to solve it for, and it's usually your choice as well, I'm going to solve one of the equations for one of the variables, and then I'm going to go to the other equation, and I'm going to perform that substitution. So if I'm just going to rewrite this as 6x plus 2 times y. Now y is now negative 3x plus 1. So I rewrite the top equation replacing y with what it equals in terms of x. And so now I carry out the algebra. I want to solve this equation. So we're going back to the things we've done earlier in this course. So I'm going to have 6x. When I distribute the 2, I'm going to have a minus 6x plus 2 equals 7. If I simplify any more, and here's what goes on with this one, that's a little alarming. Both variables disappear because 6x and minus 6x will cancel. I'm left with a statement 2 equals 7. So the very first example we have here is going to give us a special circumstance. Let me put an asterisk there for this. Anytime that you're solving a system of equations, whether you're using substitution or elimination, if both variables basically disappear in the solution process. Now, it shouldn't happen all the time, but I mean, there are going to be problems there where it's going to happen. If both variables disappear, then I have a special case. Hence, I'm putting the asterisk here. The special cases are the two things that were mentioned before, having either no solution or an infinite number of solutions. The question is, what information do I have here that'll let me know which one of the two it is? Because everyone thinks automatically it's going to be no solution, no solution, no solution. In this case, it is no solution, and the reason why is because this statement that was left is false. 2 does not equal 7. This is basically saying for these to have a solution, 2 has to equal 7. It doesn't, so it's a false statement. So that tells me it's no solution. If I were to graph these lines, I would see that they're parallel. And so, using terminology, they're inconsistent. Now, they're not asking for the terminology. You will be asked for it. We don't usually say inconsistent and independent. I mean, the independent means I would see two separate lines. The inconsistent means that they're not going to intersect anywhere, so that's the inconsistent part. Inconsistent automatically assumes that they're independent of each other. So that would be an instance where I have no solution. In B, there will be a solution. I'll give you that much. So what I want you to do is give it a try. Try to see if you can make a substitution and solve the equation, the system of equations, and come up with an answer. One of the things that sometimes causes students difficulty with this is that you have many different alternatives to do and choices to make as you do this. And obviously, if I'm going to use substitution to solve this system of equations, I have to first pick, okay, which equation am I going to solve for one of the variables, and which variable am I going to solve it for? I mean, technically, theoretically, I could solve the top equation for x or the top equation for y. It doesn't matter. I could do the same thing for the second equation. I can solve it for x or solve it for y. The choice that I tend to make is based off of, well, what's the easiest of them to do? Which one requires the least amount of steps? If I solve for 3x or solve for x or y in a top equation, I'm going to have to carry through a subtraction on both sides and a division and get some nasty looking fractions as a result. Because when I divide both sides by 5, the 31 and -3 I'll have on the other side, they don't divide by 5 evenly. So I'm going to have decimals involved or fractions, and that could cause some grief. Same thing if I were to solve the bottom equation for y. I would have to subtract the x from both sides and then divide both sides by 2, which would bring about fractions in it. The fact that I have, this x with nothing in front of it is what would lead me to say, okay, I'm going to solve this one for x. And it only takes one step. X is -2y plus 11. So I have that set up to do my substitution, so I go back to the first equation. Now, as I said, is it wrong for me to solve the bottom equation for y instead? No. Is it wrong for me to solve the top equation for x or y instead? No. It's just a little bit more complicated, that route. And so, I often make the choice based off of which one's more or less complicated. I'll tell you with all honesty, this is one I might have usually chosen to do elimination on. But substitution is not too bad for this one either. So I'm going to go to the top equation. I'm going to replace the x with -2y plus 11 plus 5y. Everything else is being left alone in the top equation. I'm just replacing what the x is. When I distribute the 3, I'm going to have -6y plus 11 plus 5y equaling 31. Oh, take that back. This should be 33. I said distribute, but I didn't do it. So, uh, negative 6y plus 5y would be negative y plus 33 equals 31. Negative y, when I subtract 33 from both sides, it'll give me a negative 2, which means y would be 2. Now, with this, I know what the y value is. The easiest thing now to do is to come back up to here, to the x equation, and substitute in for the y. And so when I do that, x equals negative 4 plus 11, which means that x is going to equal 7. And so oftentimes you're going to be asked to write that as an ordered pair, because remember, this is representing the intersection point of these two lines, but it's also telling me the x and y that makes both true at the same time. And again, this would be an instance of being consistent and independent. So you can see how this works, although when I circled this over here, my 7 kind of disappeared. And I could see how a special case can show up and how to make the conclusion. When I do elimination, which is the other method that we make use of to solve a system of linear equations, and the one I most often use, we're going to have, the same kind of situations come up. There's some things that are good about it, some things that might be more complicated for some people, because there's things you have to keep in mind. But usually it works down to the point where I end up with an equation to solve for one of the variables. It's just a one-step equation after that point, whereas oftentimes with this, I'm going to end up with a two-step or multi-step equation to solve. So that's why a lot of people like elimination. And I make very similar conclusions if I have special circumstances with that as well. So let's have a look and see how we do some with elimination by going to do example 3. So when I solve equations using elimination, what I am going to try to do is I want to take, first of all, it's going to be in this expanded form. And I do want my x's and y's to line up. So if I have, an equation that starts with an x and goes to y equaling a number, and I have another one that starts with y and then the x equaling a number, I want to rearrange and make sure I keep the signs where they belong, rearrange it so that my x's and y's line up. And when we do other solution methods as we move through this chapter, it's going to be very important to do that for other reasons as well. And we'll talk about that when we get to those. For elimination, and the reason why it's also known as the linear combination method, is because if I add two equations together, if there's a true solution for both of these equations in A, if I add them together, I would get yet another equation that should share the same solution. So, that could be very helpful in some cases, but, if I have another one that just has an x and a y term in it, it doesn't really help me a whole lot. And that's because all I'm going to do is have a third equation that has the same solution, but not really know how to get to that solution. Ideally, what I want to be able to do is add the two equations together, combine the two equations, and have one of the variables disappear, cancel out, go away. So I can do some manipulation of this to make that happen. So what I usually have to do is I have to choose a variable that I want to eliminate. And then what I want you to do eventually is get the same number in front of that variable, but have different signs. And again, I make the choice about what I do based off of what's there and which would be the easiest to get to that situation where I would have the same number in front of the x's, with one being the opposite of the other, or the same number in front of the y's with one being the opposite of each other. So there's different ways you can go, but oftentimes there's going to be one that's a little easier than the others. So for instance, I notice that, well, I have a 4 in front of the x and a 5 in front of the x on the second equation. These don't have any factors in common. They have multiples in common. I could say, okay, well, if they're both 20x, I can go through and solve this and so forth and so on and make the appropriate adjustments. But, I had to alter both equations. Not that it's wrong to do so. It's just more work than necessary, because if I look at the y's, I have a 3 in front of the y on top and a 6 in front of the y on the bottom. 3 is a factor of 6. I also notice that the y's also have opposite signs, whereas the x's are both positive. And if I have both being positive, I'd have to multiply one by a negative, and I have to choose which one it is, and then make sure I'm distributing that negative correctly. So usually, if you're choosing a method that has more steps to it in the setup process, you are creating a circumstance where you have more opportunities to make errors. And so that's why I usually recommend trying to find the one that requires the least amount of work to do. It won't be wrong if you go another route. Matter of fact, there will be some systems of equations that you have to alter both equations if you're using elimination, or if you choose to do substitution. You're going to have some nasty fractions in it, and you have to deal with it. So what I'm going to do is I'm going to take the top equation, and I'm going to multiply it by 2 so that I can change the minus 3y eventually into a minus 6y. Now the thing is, I just can't change the y term. I have to change everything. I have to multiply both sides in their entirety by that 2. And that should be a 9 in there, not a negative 9. In the second equation, I'm not doing anything to it. And so when I get my new system, since I'm multiplying both sides of the top equation by 2, I'm still making it equal. I'm making yet another equation that's going to have the exact same solution, but this one will combine better with the 5x plus 6y equaling 8, because I'm going to have 8x minus 6y equals a negative 18. And here I'm going to have 10x plus 6y equaling a negative 8. And I don't need to change the bottom one. I got multiplying by 2 happy. That stays the same. And so when I add the two equations together, 8x plus 5x is 13x. The minus 6y and the plus 6y cancel, and they should. Something should cancel. If you didn't get anything to cancel when you're adding the two, when you get to the step of adding the two equations together, then you haven't set it up correctly. One of the variables should cancel. And remember that for them to cancel, they have to have opposite signs. I will have students that will get a plus 6y on top, and and then they'll say when I add them together they cancel. Well, no, if you add plus 6y and plus 6y, it's 12y. So make sure your signage is where it's supposed to be as well. And this is going to equal negative 18 plus negative 8 is a negative 26. When I divide both sides by 13, I get x is equal to negative 2. So I got my first value for one of the variables. Now what I do is I go back to one of the original equations. It really doesn't matter which one it is. I chose the top one. And I'm going to say, okay, I'm going to have 4 times negative 2 minus 3y equals negative 9, which means I have negative 8 minus 3y equaling negative 9. Adding 8 to both sides, I have negative 3y equals negative 1. And dividing both sides by a negative 3, I would get 1/3. So my solution is negative 2, comma 1/3. And 1/3 might have been one that if you were graphing it, you wouldn't necessarily pick that as being the answer unless you happen to be plotting things by thirds and having a scaling by thirds. You may not have noticed that. You would see it somewhere between 0 and 1 where the y coordinate would be, but you'd be guessing otherwise, where this is giving you the exact value of 1/3. And of course, this is consistent and independent. Now for your turn, I want you to go to part B, and I want you to solve that system of equations. A big hint, if you look at this, the 3x and 4x, they don't have any factors in common. The negative 6, or multiples in common, really. I mean, one's not a factor of the other, I should say. And negative 6 and negative 8, one's not the factor of the other either. So it looks as though I'm going to have to change both equations in some way. So as you do that, make sure that, notice that both the x's and y's have the same sign, so one of them has to be multiplied by a negative, whatever it is you choose, and to get whatever variable to cancel along the way. So make sure you choose a variable and come up with a good way of getting rid of it and carry through this process. And then let me know what you get as an answer. Okay, so with this, we have 3x minus 6y equaling 9 and 4x minus 8y equaling 12. And as I mentioned before, I don't have a situation where one of the coefficients on the x is a factor of the other, and the same thing with the y's. So I'm not going to be able just to make one change to one of the equations and that's it. I'm going to have to change both equations. What I chose to do is essentially I chose to eliminate the x's. So the first number that both 3 and 4 can had the least common factor between the two is 12. So I like to get a 12x in front of each one of them, and one of them I like to be negative. So I chose the bottom equation for that to happen. So what I did when I set this up is I said, okay, the top equation, I'm going to take 4 times the 3x minus 6y equaling 9. And I did negative 3 times the 4x minus 8y equaling 12. Remembering that I had to multiply this by the 4 and this by negative 3 as well. I almost forgot to write that. When I carry through the stuff on the top, because I want to simplify my system before I start trying to solve it, I have 12x minus 24y equaling 36. On the bottom I have negative 12x plus 24y equaling a negative 36. When I add these together, my x's do cancel. Great. But so do my y's. In actuality, so do the numbers I have on the right-hand side. So essentially, on the left, when I carry through this addition, I have nothing. On the right, I also have nothing. This is a special case. Both variables disappeared. So I know I have a special case. That's how I know. This statement, compared to the one we had in example 2 with the substitution, this is a true statement. True. 0 does in fact equal 0. And so if I get a situation where I have to conclude that there is a special circumstance and I end up with a true statement, that indicates that I have infinite solutions. And that means that I would say this is consistent and dependent. Essentially, the two equations I have are of the exact same line. Therefore, they're going to intersect each other everywhere. And so that's how you go through these two processes. We're going to see a couple more of these processes as we go through and do some of the word problem examples for the rest of this. So you'll have a chance to try out your ability to, well, we have one more example, your ability to solve a system of equations using one of these two methods to come up with an answer. So let's have a look at example 4 and see how we can apply this to a word problem circumstance. So we have this word problem now for example 4. Dawn works for a computer store which sells Macs and PCs. She earns, on average, a $100 commission for each Mac she sells and $135 commission on each PC she sells. During the last month, she sold 26 computers for a total of $3,090 in commissions. How many of each type of computer did she sell? So take a moment, see if you can set up a system of equations that represents this circumstance and solve it to answer the question, and then we'll go through this. Okay, so Ultimately, what I'm looking for here is I want to come up with a system of equations that I can solve to answer this. So I'm going to show how I usually go through and dissect a problem like this so that maybe you can mimic it and try other ones in the same way. But it does take information about reading it and making sure you know what it is information you got versus what you are looking for. Ultimately, what we're looking for here is how many of each type of computer that Dawn sold. So that's what I'm going to let my X and Y be. I'm going to let X, I'm going to just use M and P. M is going to equal the number of Macs sold, and P is going to be the number of PCs sold. You can make them X and Y, you can make them any letters or symbols you want as long as you know which one represents which. So let's take a look and see what information that we have here. There's two things that we're looking for, because I mean there's only two types of computers they're mentioning, and they're looking for how much she sold of each. So I have two values I'm looking for, which means I need to come up with two equations that relates these two together. So one equation is the fact that she sold 26 computers were sold. That means that the number of Macs that she has plus the number of PCs that she sold should total 26. The other one is kind of split up in several different spots. So let's have a look at it. It has to do with her commissions. She earned a total of $3,090 in commissions. Put the total here. She has a $100 commission for each Mac and a $135 commission on each PC. So if I want to figure out how much of a commission she earned on the Macs only, I would take 100 times the number of Macs she sold, which in this case is M, because we don't know what it is yet. So 100M would be how much money she earned off of the Macs that she sold. Whereas 135P would be the amount of commission she earned from the PC she sold. And obviously those two values together should total the 3,090 that she actually got with the commissions. So there is our system of equations. So now, how do I go about solving this? Now, you could have solved it any different number of ways. It doesn't matter which way that you chose to do it. You could choose to have done elimination. I'm going to choose to do substitution. The top equation would probably be the easiest to solve for one of the two variables, so that's the one I'm going to solve. It wouldn't be wrong if you tried to solve the bottom equation for one of the two variables if you also chose substitution. And it's just as easy for one of the variables than the other, so it doesn't matter which one that you would choose in this one as far as ease goes. I chose to solve for P. And so I changed this equation here into P equals 26 minus M. Because now what I'm going to do is I'm going to use this and substitute into the bottom equation now. So coming here and coming here, when I rewrite the equation, I'm going to have 100M plus 135. I'm going to replace P with what it equals. P is being replaced. Equals 3,090. I'm going to simplify this equation before I start trying to solve for M, because I want to get M alone on one side. So I'm going to distribute the 135. 26 times 135 is 3,510 minus 135M equals 3,090. 100M minus 135M is a negative 35M. plus 3,510 equaling 3,090. Now I have I have one variable m now, so I can use the rest of the basic equation solving techniques. I'm going to subtract 3,510 from both sides, and I'm going to get 35m equals a negative 420. And then when I divide both sides by negative 35, I get 12. So she sold 12 Macs, which means now, if I come up to this equation again, that's going to be 26 minus 12, which equals 14. So based on the information that we were gathering here, and now we go back and make sure, am I answering the question that they asked for? Sometimes they may ask us how many PCs did she sell. They might ask how many of the other ones she sold. In this case, they're asking for both. So answer the question that's always given. Dawn sold 14 PCs and 12 Macs last month. And that's how you go through and do it. So again, you could use different methods of solving your system of equations. Hopefully you did come up with this system of equations, because that's what the information gave us. And then from there, there's different routes you can take based off of what method you want to use, which variable that you're going to either eliminate, or which variable you're going to solve for, which equation you're going to use of the two. I mean, so there's a lot of decisions that could be made that could alter the path you're going to, but they should all lead to the same answer regardless. If you have any further questions with this, please make sure to reach out to me or come to my office hours or ask about them in class. Until I see you in one of those places, or until the next video, I will see you around, and have a good day.